Hi there. We're on to chapter 13. Let me see. Where is that? I'm going to share my screen here. And this guy is really interested in what we're going to talk about next. Hopefully, we don't scare him too much with all this math. He is cute though, isn't he? All right. So for this chapter, you should have a very clear understanding of what we learned in the last chapter for analysis of variance, of course, because as the name would suggest, two-factor analysis of variance, we are building very much so upon the last chapter and what we learned in there. And also, we should understand what individual differences mean from page 347 in your book. All right, so when it comes to analysis of variance, it evaluates differences among two or more sample means. And for the last chapter that we looked at, we were looking at how to calculate ANOVA if we had only one factor, right? And remember, when we say factor, we're talking about independent variables, right? We're using a little bit different vocabulary uh, for this type of statistical test. All right. And you can also make comparisons for experimental conditions as well as quasi-independent variables, right? Whether or not experimental. Say you wanted to make comparisons between ethnic groups, right? That's not experimental. All right. And so here we have independent measures that uses a separate sample for each treatment condition being compared. And here, this is a single factor, one-way ANOVA, and they're comparing for time of day, and they had three conditions, right? Morning, noon, and evening. So that's just one factor. Here's what it looks like when you have two factors. And we've kind of seen this in the last chapter. We mentioned this was coming, so you were forewarned. So, and this is more complex. There's more steps, I should say. I mean, and so it'll be important to, keep pretty organized when going through this formula. All right, so here we have now for a factorial ANOVA, we have two independent variables, and they can be manipulated. So for this example, we have time of day and whether or not someone had consumed caffeine. Both independent variables and quasi-independent variables may be employed as factors in a two-factor ANOVA. Remember, let's see, I already mentioned that. Uh, ah, uh, so here we go. We have a two-factor ANOVA allows us to examine three types of mean differences within one analysis. And by the way, when we're talking about a 2x2 factorial design, these twos represent a factor, right? So this means I have one factor that has two conditions and I have another factor that has two conditions. Well, I can also make this a little more complicated and add the number of conditions for each factor. I can have a 3x2 factorial ANOVA, where one of my factors has three conditions. I can have a 3x3, which would mean both of my factors have three conditions each, and so on. It can get more and more complicated. And in fact, I can add the number of factors. I can have more than just two factors as well. Like I mentioned, it can get more complicated, but we are just going to learn about two-factor designs only, and also we'll be looking at how to calculate where each of the groups or conditions have an equal number of people in each of them, all right? All right, so, and we will also be looking at the joint impact of factors when they're considered together and how they affect your independent or your dependent variable, pardon me. All right, so to do that, we will look at three hypotheses when we're looking at the 3F ratio. So we'll be calculating 3 different F ratios and seeing how they all work together. All right, so the 3 F ratios have the same basic structure. The numerator measures treatment mean differences, and the denominator measures treatment mean differences when there's no treatment effect. All right, so the first thing we look at when we're doing a factorial ANOVA is our main effects. And that's when we're just looking at if there are mean differences among levels of just one factor. So we're considering only one independent variable or one factor at a time. And we're trying to determine if there are any differences between the levels in that just that one factor that you're looking at. So, oh God, what? Can't you hear me? Didn't you hear me? I'm sitting there talking. I'm recording. If we're looking at the design or the table below, it'll be like looking at one factor at a time. So say I'm looking at the independent variable or the factor for the amount of time spent in instruction. And we have 2 levels, 4 hours and 1 hour. And I would look at the means for each of those levels and determine if there's a difference between them. And I would do the same. And this is not, pardon me, this is not making any comparisons or taking any consideration for the other factor, which is setting in this example. But when I'm looking at main effects, I want to look at each factor individually for all of the factors involved. So after looking to see if there's a difference between the time and instruction, I would then look to see if there's a difference in setting for the other factor. All right. So the main effects provide information about the effect of each independent variable taken by itself. So here we would say there was a main effect of time in instruction, and there probably was. It looks like the mean for this one is much smaller than the mean for the other one. So the main effect of each independent variable is the overall relationship between that independent variable and the dependent variable. In a design with 2 independent variables or with 2 factors, there are 2 possible main effects, one for each independent variable. If I was doing a factorial ANOVA that had 3 factors, then there would be a possibility of 3 main effects. Okay. All right. So the other thing that we look at beside main effects are interactions. And that's the mean differences between individual treatment conditions or cells and they are different from what would be predicted from the overall main effects of the factors. So if there's an interaction when you do an ANOVA between two independent variables, the effect of one independent variable depends on the particular level of the other independent variable. So here is when we are taking both factors or both independent variables into consideration and to see how they are working together, or if they are working together to affect the dependent variable. So that's when we're looking at the means here, right? So this mean, for example, is the mean for the in-class level and the 4 hours of time in instruction. It's taking those two into consideration. And the same is for each of these cells. So when I'm looking at interactions, I'm trying to see if there's a difference between all of these here. All right, so an interaction can be defined as a unique effect of two factors working together. When we think about real life and, events that occur, usually when something happens, it's not the fault of just one thing. It's not the result of just one thing happening. Usually it's a combination of things that cause an event to happen, right? And so factorial ANOVAs are kind of trying to get at that. It's trying to discover what are the several things that need to exist in order for an effect to occur, right? It's kind of trying to mimic real life a little better. Although it's not perfect, it's still kind of heading in that direction. So, like, why does someone become poor? Well, that can be for many reasons, right? Not just one. All right, so alternative definitions for an interaction actually exist, and these are just sort of viewing it from slightly different perspectives. And one is that if the two factors are independent, so one factor doesn't influence the effect of the other, then there's no interaction. Also, when the two factors are not independent, so the effect of one factor depends on the other, then there is an interaction. In fact, the main reason we do factorial designs is to see if there is an interaction, right? All right, so interactions are based on the dependence of the factors upon each other. So the effect of one factor depends on the level or value of the other factor. So unique combinations of the factors produce unique effects. Interaction can be observed in a graph. When you see non-parallel lines, so say you graph the means for each factor, and then you view it on a chart, and you see non-parallel lines, and these are like lines that are crossing or they're converging into one another or diverging. That can indicate that you have an interaction. And we would call it an A-B interaction or A by B interaction, which that's the terminology. And so visually speaking, this is what it would look like. So we were looking at a chart with two factors that had time, in instruction, as well as the setting, like whether they were in class and out of class, right? And so if we were to plot the lines as the time spent in instruction and the setting on the x-axis, we would, and then we plotted their means. So we have the means for out and in, so we have the means of 5, 5, 7, and 7, and we plotted these lines. Well, you can see that the lines themselves are overlapping. You can only see the blue line here, but that is because the lines are overlapping. However, you can see that it is lower for the out of class. Their scores are lower in the out of class condition compared to the in-class condition. So since the lines are tilted, you can say there is one main effect, right? Remember, another indication that there is a main effect is that the lines are spread out. So if we were to swap it out, right, we use the lines as the setting instead of the time in class, and the x-axis as the time in class. Now, instead of overlapping and tilting, they're just flat and separated. We can see that there is just one main effect. They're not tilted, but they're spread apart. So that tells me that there is one main effect. And here, this is an example of there being a main effect for setting, right? There's a difference. There's higher scores for time spent in class compared to time spent outside of class studying. Well, if we were to change which variable has a main effect to the time spent on studying, then you would see the scenario seen below here. And same things, split apart lines, but they're flat, or they're overlapping but tilted. And these examples are of when you have only one main effect, what that would look like. Here is what it would look like if you have two main effects. Not only are the lines tilted, but they are also spread apart. So we have higher scores in the in-class setting, as well as more time spent studying. So more time spent studying and in class yielded the highest scores. But there is a significant difference for both factors. So there's two main effects. What if you had no main effects, or what we would term as the null outcome, meaning there's no difference between conditions? You would see lines that are both overlapping and flat. And you could see by the means, they're all identical, right? So what do interaction effects look like? Well, interaction effects exists when differences on one factor depend on the level you are on another factor. It's important to know that an interaction is between the factors and not the levels. So we wouldn't say there's an interaction between 4 hours a week and in-class treatment. Instead, we would say that there's an interaction between time and setting, and then we would go on to describe the specific levels involved. There's three ways to tell if you have an interaction. One is to just run a statistical test. Say you pop everything into SPSS or some other statistical program and do the test, and you find significant results. Or you calculate it all by hand. I think some people prefer doing it in SPSS, but I digress. Also, you can tell that you have a significant interaction when you can't talk about the effect of one factor without mentioning the other factors. So if you can say that time in instruction makes a difference, then you know that you have a main effect and not an interaction, because you did not have to mention the setting factor when describing the results for the time. On the other hand, when you have an interaction, it's impossible to describe the results accurately without mentioning both factors. Also, you could tell if you have an interaction if you can spot it after graphing the group means. So whenever there are lines that are not parallel, there is an interaction present usually. Here you can see in the graphs interaction. Here's an example of an interaction, right? You have lines that are tilting and they are spread apart. So you probably have a main effect, and they're also crossing or converging or diverging, I should say, if you're looking at it the other direction. And you can tell that they've graphed the means here. So we have the same means for end of class as well as time and instruction, but they're different if it's spent in class and when compared to whether they spent 1 hour or 4 hours, right? You have a much different outcomes when the more time spent in class. If you notice, I just mentioned both factors all at once. All right. And you can tell visually they're converging down here in the corner. All right. What if you have another scenario is you can have an interaction without main effects, with no main effects, right? There's no differences between the levels for each factor, but you can also still have an interaction. And when that is the case, you would see a chart that looks like the one down here. It's like a perfect X, right? And the chart for that would kind of look like this, right? Okay, so you can see it's like makes a box. All right, so not only can we graph them using a line chart like you see in the ones we've been looking at, but you can also do it using bar charts because these are categorical variables, right? High, low food intake in this case versus sociable and unsociable, and whatever they're being measured on. And the way you can evaluate whether you have main effects or interactions, I should say, is if I were to draw a line from the top of this blue bar to the top of the other bar, and then do the same for the orange bars, I would see that the lines here are crossing. So that would indicate to me that I have an interaction. Okay, so like I mentioned before, when you are doing factorial ANOVA, if you are doing 3 distinct tests. You're looking for the main effect for in the case of a 2 by 2 factorial ANOVA, which is what we're looking at here, or 2 factors in a factorial ANOVA. You're looking for whether there's a main effect for the first factor, if there's a main effect for the second factor, and if there's an interaction effect. All right, and you need to do a separate F-test for each possibility. All right, so let's do our first learning a check. Which of the following accurately describes an interaction between 2 variables? All right, pause the video and see if you can guess what that might be. All right, and the answer is D. The effect of one variable depends on the level of the second variable. Levels. All right, so here is, we're looking at what it might look like, the chart, if we were to graph these. And so if you have an effect or a main effect for A, it evaluates the mean differences between the rows, right? The 1 and the 5. And if you had a and so in this case for A, the 1 and 5 you can see are charted right here. And if you had a main effect for factor B, you would evaluate the means for that as well. If you have a A-B interaction, we're looking at the differences between the boxes within here. So because you're getting the mean for each level of each factor. Oops. All right, so the first stage when we're calculating for factorial ANOVA, it's identical to an independent samples ANOVA, where you compute the sum of squares total between and within treatments. Then the second is to partition the sum of squares between the treatments into 3 separate components that compute differences that are attributed to factor A, factor B, and then the AB interaction, which is any remaining mean differences that define the interaction. It's kind of like whatever is left over. All right, so just to review the notation for ANOVA, and oops, there's no difference here from the last chapter. It's just a review. And so recall that treatment conditions or the groups for each factor are referred to as K. Also, the number of scores in each treatment is a lowercase n, and the total number of scores is uppercase N. Sum of squares for each treatment is T, and then the grand total was G, which is where you sum up the sum of the total from the groups. Right, and we do the same 4 steps. State your hypothesis, select an alpha level, find your critical region, compute the F ratios, make a decision. All right, so we're gonna look at the formulas, and these are just screenshots from the key points that I found in the MindTap videos. And by the way, you know, so far I've been giving you little clips of videos from others. You can look at the videos in MindTap for all of the tests. I've just been giving you additional ones, but when I looked for videos for the Factorial ANOVA, frankly, the one that's provided to you in MindTap, it was the very best one that I could find. It's very simplified, lays it out, easy to understand. So I'd recommend really watching that one to help you practice and understand the steps and how it's all calculated. All right, so so we have we first must calculate the degrees of freedom here, and to do so, for the degrees of freedom total is just the total n minus 1, and then you do that for the between treatments. And remember, we're looking at groups or conditions that have an equal number of participants for all of them. So you just really got to do it for one, and that is the number of groups minus 1. And so you can see for each possible condition across the top, we have a factor with 3 conditions where they're being given some kind of medication. And one group has 0 milligrams, others it's 50 milligrams, and another it's 100 milligrams. The other factor or independent variable has 2 conditions. One is high school students, the other is college students. So when we're looking at them together, each group consists of 6 people. Okay, so that's how you, and so it might help for you to sort of draw things out when you're doing this as well. So that is degrees of freedom for between treatments. The degrees of freedom within treatments, you just take the degrees of freedom inside each treatment, right? And so there's 1, 2, 3, 4, 5, 6 conditions, right? And so each of these conditions is minus 1. You add all of that up, you end up with 30. And by the way, you can tell how many conditions you have simply by multiplying. So what if I had a factorial ANOVA that had 2 factors, and each factor had 3 conditions instead of a 2 by 3? Well, if I were to draw that out, maybe I added another condition down here, and then I could count 1, 2, 3, and I would find I had 9, right? Well, I could also just say, well, it's a 3 by 3 factorial ANOVA is just 3 times 3 equals n, or equals a total n. And you'll find that that is true for however many factors and however many levels you add. It's just a case of multiplying. All right, so then we need to calculate degrees of freedom for each factor. Now we take for the first factor, the number of rows minus 1. So we have 1, 2 at minus 1. So we have, or you might say it's the number of conditions minus 1. Also, same thing for the other one, number of conditions minus 1. And to calculate for the interaction, you take the degrees of freedom for between minus the degrees of freedom for both factors added together. All right, and you would arrive at 2. All right, sum of squares formulas. I'm sure you were really looking forward to this. All right, so for sum of squares total, we have each score squared and then added up minus the grand total squared divided by n. For the sum of squares within treatments, which is error, it's the sum of squares for inside each treatment added up. Then the sum of squares between treatments is the sum of squares total minus the sum of squares within. So that makes it easier, right? So you only have to calculate within and total, really. All right. And so here it just sort of, I laid out the formulas for each of these calculations to show you where you're getting the numbers from, okay? Sort of help you visualize it. All right, once you have calculated for some squares for each of the factors, as well as the degrees of freedom and for interaction, you can calculate the mean squares within treatments, the error, right? So the sum of squares within treatments divided by the degrees of freedom within treatments. And do the same for between. And you can see how you arrive at the F ratio for each factor as well as the interaction. And like I mentioned before, use the demonstration video in MindTap to see specifically how to calculate for the two-factor ANOVA. It's a little difficult to do it in a PowerPoint online. I don't have the equipment or the type of programs to show how to do that specifically. So like I mentioned, use that one. But I did take some screen grabs from what you're going to find in MindTap to show you where all of these numbers are coming from for this factorial ANOVA. So you can see a little bit about it here in this lecture. So for sum of squares within, you're adding up the sum of squares. So if we look at, we're getting a 7 plus 8 plus 8 plus 9. And you can see they're doing it within each of these squares. Here's the 7 for the sum of squares when you're looking at B1 and A1, and then also for A1 and B2, and so on. And then those are added up, okay? For between, you're subtracting the sum of squares within from the sum of squares total. So we've already did the within part. So how do you do the total? Well, that's taking each score, squaring them, adding them up, and then minus the grand total squared divided by n. All right. And so you will see that the outcome here ends up being 87. All right. All right. Oh, and the shortcut, pardon me, for the total was just adding the within and the between is another way to do it. Okay, so between equaled 55. And you can see the sum of squares for factor 8. So in this first step, we were just looking at sum of squares within each group, between each group, and the total. And now you have to do this for the factors, right? So sum of squares A, and this is so we can test for main effects for each factor and then the interaction. And you can see where we're getting these calculations from, right? So it's the total from each group squared, you add them, and you subtract the grand total squared divided by n, you end up with 5. And you do the same thing for the other factor. And remember, that had 3 groups. And then the sum of squares between, which is just simply adding the two calculations from above and subtracting from the grand total. All right, and hence we have a lot of degrees of freedom to consider now. And of course, we've already went over the steps to determine what the degrees of freedom are for each of these areas. And then we just plug in these outcomes in our mean squares. So we have sum of squares from A divided by the degrees of freedom A to get our mean squares for factor A. Do the same for factor B. And then we do the same for the interaction. And we can calculate we also need to calculate mean squares within, and we end up with 2. And then we can plug in all those scores to finally arrive at our F statistics for each factor as well as the interaction. And we can evaluate for alpha 0.05. All right. All right, let's see. Degrees of freedom within equals 16. So therefore, the degrees of freedom for all is 1 and 16. In the critical region, that would be to look up our critical region, which was 4.49. And this step should have been done before actually all of these calculations. But then we need to evaluate which areas were significant using our critical region. All right, so here's a learning check 2. Which of the following accurately describes the two stages of a two-factor ANOVA? And remember, it's going to take a little while to sort of get a feel for the steps that are involved because there's so many of them required for a factorial ANOVA. So I highly recommend watching that video several times until you feel very comfortable with it. So what's our question? Let me go back. Which of the following accurately describes the two stages of a two-factor ANOVA? It is the first stage partitions total variability. The second stage partitions the between treatment variability. All right. I know you probably thought maybe we'd get away with not having to look at effect size for factorial ANOVA, but if that's what you thought, that is not correct. So we also compute eta squared for factorial ANOVA, and that's the percentage of variance explained by the treatment effects. And we do this for main effects and the interaction. And so we compute eta squared based on the partitioned variability for between subjects in the numerator. And we often call this the partial eta squared because we remove any variability that can be explained by other sources within the denominator before we calculate the percentage for each of the 3 specific treatment effects. So remember that's the 2 main effects as well as the interaction. And you can see how it's calculated below. And there's 2 ways to do it. Actually, you can do it using the first formula here, which is identical to this formula. All right, so whatever you find easier for you. All right. Here is an example of measuring effect size for the two-factor ANOVA. Here's factor A, and you can see it takes the mean squares divided by the mean squares plus the within, and then we end up for factor A to be 0.2. Factor B was 0.36. The interaction is 0.36. So the interaction, well, for each of these, the way you would state it in a sentence or what it really means is that for factor A, it accounts for 20% of the variance explained by the treatment effect. Factor B explains 36% of the variance, and the interaction accounts for 36% of the variance in the treatment by the treatment effect. All right, so we also need to report, factorial ANOVAs using APA format, and we can see an example of it here. And so first, you have to report the means, the standard deviation for each of the groups, for each of the factors, and then report the results for all three hypothesis tests. And so for each, you include the F statistic, degrees of freedom, p-value, as well as effect size. So here's an example. If you're using a 2x2 ANOVA, you might say a 2x2 ANOVA, which was gender and friendliness level, was conducted on the quiz scores. Neither gender, and it gives the outcomes. So F with degrees of freedom equaled 0. And the p-value as well as eta, nor friendliness level, and then it gives the results of that, had a statistically significant impact on quiz scores. So those right there, these first two mentions are actually mentioning main effects. It's saying there was no difference for gender, and there was no difference for the other factor of friendliness. But then the last part states that the interaction was statistically significant. So it probably, if you graphed it out, it probably looked like a perfect X, remember? And then they give the outcome for that interaction as well as effect size here. All right, so significant interactions, if you happen to have one, requires particular attention. So even if you understand what main effects are, interactions go beyond what main effects alone can explain. And so the focus on it, if you have one, is the overall pattern of results and how the different levels of each factor are working together to exert their effects on the dependent variable. And it takes a lot of practice a lot of times to really articulate what the results mean and how they're affecting the dependent variable. All right, so here's an example of what it might look like if you were to interpret an interaction. So here for this example, the difference among or between browsing Facebook and browsing a news website depends on the strength of the participants' relationship with their Facebook friends. There's little or no difference between Facebook and news when their relationships are weak. However, browsing Facebook produces much higher self-esteem scores when participants had strong ties to their Facebook friends. Therefore, the difference between browsing Facebook and browsing a news website depends on the strength of the relationship, right? And so you can see they're trying to explain the difference we're seeing here compared to when there's really no difference here when there's a weak relationship. All right, so if you do have an interaction, you need to go yet another step. I know. Just like with one factor ANOVA and doing post hoc tests, for a factorial ANOVA, two-factor ANOVA, we need to report further to understand it better. So we need to test what is known as simple main effects. And so this is where the mean differences within one column or row show a different pattern than the mean differences within another column or row. And it's a separate analysis for each of the individual columns or rows. For example, we test for significant mean differences between Facebook versus news browsing for the strong relationship condition. So really it's making comparisons between all these possibilities, right? It's seeing is there a difference between these two cells? Also, you would look for a difference between these two cells and these two cells and these two cells. All right, so the good news is you've already calculated in the original ANOVA equation the numbers that you need for evaluating the simple main effects. So you can take the formula for the simple main effects and plug in the numbers you've already found, all right? And so you can see here for this, it's the variance or differences for the means in column 2, divided by the variance and differences expected by chance. All right, and this equals the mean squares between for the two treatments in column 2, divided by MS mean squares within from the original ANOVA. So you state the null and determine alpha. And in this case, the null would be M Facebook equals M news, or the mean for Facebook equals the mean for news. And the alpha is 0.05. All right, and you can see the calculations that are done here, or the formulas, I should say. And so the SS between comes from the two treatment totals. So for the first one, the group T was a 125 and the other group was 75, and these two are compared. Each of these totals are based on 5 scores, and the two totals add up to a grand total of 200. Because this SS value is based on only 2 treatments, it has a degrees of freedom of 1. Also, the mean squares within equals 20, with a degrees of freedom of 16, and this comes from the original ANOVA. With a degrees of freedom of 1 and 16, the critical value is 4.49, so we have a significant result here. All right, so here you can see it was 12.5. All right, so here's some things to consider. How Factorial ANOVA can reduce variance by using a second factor. So participant characteristics might vary quite significantly from one person to another, like age or gender. And so these characteristics can influence the scores that we obtain in a study. So a lot of times when you're doing a regular Factorial ANOVA, if you happen to know that there's some kind of participant variable that also affects your dependent variable, it might be a good idea to include that person variable, like maybe gender, in your analysis and turn your one-way ANOVA into a factorial ANOVA, so include it. So large variance tends to reduce the size of a t-statistic or F ratio, which can also reduce the likelihood of finding significant mean differences. So including a participant variable can control for this variability and increase the likelihood of finding a significance. All right, so the solution to the problem, like I mentioned before, is use that specific person variable and include it as a second factor. So instead of one group in each treatment, the researcher divides the participants into 2 separate groups within each treatment, right? So one factor consists of 2 treatments, and the second factor also has 2 treatments based on gender, right? So you end up with a 2 by 2 instead of just doing, a simple one factor ANOVA. All right. So some other assumptions that you should know about when it comes to factorial ANOVA is the validity of the ANOVA depends on 3 assumptions: that observations within each sample must be independent of each other, the populations from which the samples are selected must be normally distributed, and the populations from which the samples are selected must have equal variances, which is homogeneity of variance. All right, here's another learning check. If a 2-factor analysis of variance produces a statistically significant interaction, then you can conclude what? All right, let's find out. You can conclude that the significance of the main effects is not related to the significance of the interaction. All right, our last learning check for this chapter Is it true that two separate single-factor ANOVAs provide exactly the same information that is obtained from a two-factor analysis of variance? That's an interesting thought. All right, is it true that a disadvantage of combining two factors in an experiment is that you cannot determine how either factor would affect participants' scores if it were examined in an experiment by itself? Both are false. It's false. Main effects in a two-factor ANOVA are identical to results of two one-way ANOVAs, but a two-factor ANOVA provides interaction results too. Remember, that's why we do it. Also, it's false. The two-factor ANOVA allows you to determine the effect of one variable while controlling for the effect of the other. All right, so I provided a few slides here. I provided you a slide to sort of give you an overall visual of the formulas needed to calculate for the factorial ANOVA. Another one that's probably a good slide to print out so you can study and keep to help you learn how to do this. And I also provided the steps you would take in SPSS in order to calculate for a two-factor ANOVA. All right. And this last slide was just a continuation of those steps needed. There's a lot, not only are there a lot of steps when you calculate it by hand, there's a lot of steps when you do it in SPSS as well. All right, it was great going through this chapter with you. I look forward to seeing you next time.